361. So it says, find a function such that derivative is x cubed and the line x plus y equals 0 is tangent to f. So, how do we go about this? Well, we'll just one piece at a time. We want to find the function. The derivative is x cubed. So, using the reverse power rule, this has to be x to the fourth 4, but plus some constant, which is important. You have some flexibility in trying to we have some flexibility in trying to solve, fulfill the rest. So we have to think about how we might do that. Well, let's try putting this equation into slope-intercept form. That's y equals negative x plus 0. So the slope is negative 1. So if this is going to work, the derivative has to be negative 1, right, at some point. Well, what point? X cubed equals minus 1. Where is that? So indeed x equals minus 1. Let's find the cube root of each side. So let's see how that works. Here we have minus 1 equals 1/4 plus c. So that's a point on the function. Negative 1/4 plus c. We don't see that. And we want to look here. This is the slope is minus 1 everywhere. What value does this have at minus 1? Minus 1 is 1. So at minus 1 it has the value 1. This is just kind of looking at it analytically, but we have this function here. It's cubed. And, oh, that's the derivative. Okay. So, function f of x c is going to look something like this, except that it could move up and down. And here's our y equals, well, y equals -x. Just want to kind of get a feel for what this looks like here. Like this. So we have to kind of move this up and down so that we have a tangent at this point. Well, the place where the tangent, where the derivative of this, the slope of the tangent there, and the slope of this line match is at these 2 points. So how do we make them match? Set 1/4 plus c equals 1, or c equals 3/4. So that tells me if I move this function up 3/4, I'll be able to match, this point here, -1, -1. So this is kind of the analytical approach, which is usually the way to go, but it helps to look at the graph. This is kind of what happens. I think the big picture is that when we find an antiderivative, we're finding a family of functions, right? This is a solution. These are all solutions with this adjustable parameter. They all have the same derivative. So I think that's what that problem is about. And then having to kind of match it to some line, or the slope of some line. If you think about it, you could have pretty much given you any line here, right? Given a line, it has a slope. You can work the derivative backwards and find the slope. Find where our function has that slope, and then adjust the c parameters so that they match. Which kind of visually is, you can take any line you want, anywhere you want, and you just have to find where this slope and this slope match. And just move this up and down so it matches. All right, any questions about this or other homework problems?
Is that true that any continuous function that can be any line, any tangent?
It's a good question. Point out something about the function they gave you, x cubed. It's 1-to-1 over all real numbers. Meaning, if I give you a y, you can always find an x. So you can always find a slope. Now, what if I gave you a function where that wasn't true? Say the function z of x equals x squared. So this maps all real numbers to positive numbers. I'm sorry. I said the derivative is x squared, so that is x over 3 plus c. So this can only be positive. But if I gave you this line, where this is negative then you can't.
So it's, I was thinking of like a transcendental function, sine and cosine. That's
Oh, well, that's much worse. See, we'll just draw. So this is the derivative, sine, and so the function is negative cosine plus c. So the function now it's like this, except it can move up and down. Now this function is going to match every possible slope, right? Multiple times.
That's what I was thinking of.
So I can give you a line, and well, let's just use the same line. I know diagram's getting a little complicated. So okay, so if I move this down here, so that's a solution. But it looks like if I move this up here, that's a solution. So there becomes, because it's periodic, there's an infinite number of different solutions. Yeah, to be true for sine, cosine, tangents. I think again the trick is, to answer your question, can it work for any line, is this function 1-to-1? Does it cover all the possible slope values? Any other questions on any other remarks? All right. Clear the board here. So today, and maybe also on Tuesday, we're going to cover our first heavy-duty technique for finding antiderivatives and finding definite, indefinite integrals, which of course can be used to find definite integrals. And that technique, one of a number, is called section 5.5 substitution. And hopefully by the end of today or tomorrow, you'll be able to go home and substitute your hearts out. I have an admission here. I haven't taught this in a semester, but I decided to go back and play around a bit. I have a good book that has some really good substitution problems. And I was looking for one that would be appropriate. I will get to one later, but I don't know what it is, senility or I don't know, hadn't done it in a while. It was hard. It used up a lot of paper and made a lot of careless errors over and over. This is not easy stuff. Some of it is easy. We'll do a few easy problems, but this will work your pencil and your hand quite a bit, trying to figure these out. So, thankfully, this is the last really big hurdle in this class, and doubtful I would put a problem that you would need an hour to do at home, under the calmness of, favorite music, or maybe if you get nervous, a beer or something. Oh, wait a minute, you guys, some of you were underage, I can't say that. That would be cruel and unusual punishment. However, giving it to you on homework and trying to keep the work out, get your skills in this area, get your analytical skills working. It's a good thing, especially, I think almost everyone in here is in a major where being able to think clearly, think through puzzles, think out of the box, think inside the box, it's all good. But before we get to substitution, we need to go over a couple integral problems, because techniques, which are really straightforward, are going to be very useful. So the first indefinite integral we're going to look at for a second here is integral of 1 over x, which you should hopefully by now know is the absolute value of the log of the absolute value of x plus some constant. Now, we can do a little with this real simply. You can say, well, wait a minute, 1 over x plus some constant a is the log of the absolute value of x plus a plus some constant. Now, why can I get away with that? Well, let's do it in reverse. Let's find the derivative. Derivative of the log is whatever this function is, 1 over it, times, using the chain rule, times the derivative of this function, which is just 1 plus 0. Because the derivative of the constant is 0, it just comes out. Right? That's what we're looking for. All right, so whenever we see something that looks like this, we know the indefinite integral. We know the antiderivative. We can take this just a little bit further. We have this integral. Well, how are we gonna thread this needle? Well, this is equal to what? 1 over x plus a over b times b. Is that right? No. 1 over b. No, I'm still getting it right. Over b. Yes, okay, that's it. All right, if I multiply these two together, I end up back at bx plus a. But I can take this outside, right? Constants move outside, the integral is 1 over x plus a over b. And then we can just go back here. And what do we end up with? We end up 1 over b times the log of x plus a over b plus our movable constant c here. So in all these cases, when we get something that looks like this, we can find the indefinite integral, the antiderivative, quite easily. All right, that was kind of, I'll call that example 1. Example 2, this is a different problem. Looks like this. We have maybe x squared plus 3x plus 1 over x plus 1 dx. Now we have a lot of things that look like this. Sometimes we'll have something that looks like this. Let's see if I can get this right. And up here I have plus. And here I just immediately notice that if you look at this as integral of derivative over the function, right? Because 2x plus 3 is the derivative of this function. That I, again get this pattern. Tells me this is log of f of x plus c. You don't want to mistake these two. So, how do we go about this? Well, maybe we can make some headway by trying to divide this out. So I'm going to pull out long division. Some of you may know synthetic division works just as well in this case because this is just x plus or minus some constant. All right, so how do I do this? X goes into x squared, x times x squared plus x. I suppose I could hope this is going to come out even. I'm going to have a remainder 0. That would be nice because then I have a simple problem left. I don't have to worry about the whole at -1 because if I'm integrating some function like this and it just happens to have a hole here, that doesn't affect the area. You just can have a countably infinite number of points like that in our integration, and they don't prevent us from finding the area. But that's not going to be the case here, is it? We're going to get 2x plus 1, and x goes into 2x 2 times, 2x plus 2, and we have -1. We have remainder 1. So all right, let's rewrite this. So this becomes the integral of x plus 2 plus -1 over x plus 1. Well, take a look at that. That kind of came out nice, didn't it? Because we know how to do this. Right? We can break this up. Right? This is going to be x squared over 2 plus 2x minus, well, what have we got here? We just got log of absolute value of x plus 1. Let's see. So keep this in mind also. We're going to do this technique substitution, but sometimes we're going to end up with something like this or something like this, and we have to be aware of that. All right, again, before I go forward, any questions about this? We'll definitely come back to things that look like these examples in a few minutes. So, as is the case with most of these techniques that you may get to for solving integrals, more difficult integrals, they're usually associated with some rule of differentiation. In this case, it's the chain rule. I'm going to write the chain rule this way for the moment. dy dx equals dy du. There's du dx. Here, y is some f of x, and u is some function, some g of x. So in Newtonian notation, we would write this way. We'd say we have some function f of g of x, some composition, and we want to find its derivative. And we would find that its derivative is the derivative of f at g of x times the derivative of g at x. Repeat that, the derivative of f at g of x times the derivative of g of x. Saying exactly the same thing as this. And I guess I want you to note that here, what I'm calling u dx is the derivative of g of x. Or g prime of x. Now, I think I've said things like this before, where I say, this is just notation. It's useful notation, but it's helpful notation, but it's just notation. We can write this as du equals g prime of x dx, as if this were a fraction. It's not a fraction. You know, as far as we're concerned, this, you know, you can think of it that way, but, you know, you can think of this as like a delta u and a delta x that are really, 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 really small. But because they're infinitesimally small, this, I can only call this notation. All right. Now what we're going to do here is we're going to find the integral of both sides of this equation. So the integral of the derivative of f of x dx, well, that's, you know, we know from the fundamental theorem of calculus, that's just f of g of x. On the other side, we have integral of f prime of g of x, g prime of x, dx. Now we're going to do a substitution here. Since u is g of x, we're going to call this integral prime of u. And since we have g prime of x dx here, we're going to call that du. So this is what we call the substitution formula. We have a composition of functions, and we're kind of using the chain rule in reverse. We're going to substitute for g of x some other variable u, and we're just going to try and solve this. Now, this all depends on the fact that solving this integral is easier than solving this integral. If not, we've done this all in vain. We also have another issue, which is when we're done, we're going to get, some f of u. Gosh, that sounds like something I intentionally put in there to get people's attention. We're going to have some antiderivative in terms of u, but we may not want it in terms of u. We may want it in terms of x, in which case we're going to have to go back and substitute back to get our f of, f of g of x, which will be some other, h of x. All right, if this sounds a little abstract and complicated, that's fine. We're going to do some problems, and hopefully they will clarify how you go about this. So let's take a look at this example here. Square root of 2x plus 1 dx. What can we do? What kind of substitution can we do here that would make this look simpler? Well, an obvious choice might be, let's set u equal to 2x plus 1. Now we're going to need du dx. Well, that's just 2. Again, we can write du equals 2 dx, or dx equals 1/2 du. And then we're going to substitute here. So 2x plus 1 becomes u. Dx becomes 1/2 du. And now we have an integral that we can find the antiderivative pretty easily. Just because I find it easier, I'm going to call this u to the 1/2. So I can go ahead and use the inverse power rule, the reverse power rule. This is going to be u to the 3/2 over 3/2 times 1/2 plus our constant. This needs a little unraveling here. This is 2/3 times 1/2 u to the 3/2 plus c, or 2 to the 3/2 over 3 plus c. Of course, now we're back to that point I made earlier. You might want this in terms of x, right? So u is 2x plus 1, so this just becomes 2x plus 1 to the 3/2 over 3 plus some constant. Now that seems a little magical, and so when you do these, there's a lot of room for minor error, so it's a good idea to check. And we have a straightforward way to check this. We just look at our result and find the derivative. So let's do that. It's 2x plus 1, 3/2 plus a constant. So using the power rule here, this is going to be 3/2 2x plus 1 over 3 1/2 0. 3's are going to cancel. It does look like I went wrong. It's a factor of 2.
The applies to the numerator. The exponent 3/2 only applies to the numerator.
Oh! Thank you. That goes over here. Goes over here. Goes over here. Yay, 2x plus 1. Thank you, George.
That's not what I meant.
Huh? That's not what you meant?
No, I was just looking at the numerator there. It says 2x plus 1 with the 3 guys. It's only on the numerator, and then you wrote everything in brackets on the next line.
Wait a minute, wait a minute. No, hold on.
Yeah.
No, I made that up.
Yeah.
Let's try again here. This is 1/2, 3/2, 2/3. Should be this. Oh! Okay. It's early in the morning for me. Lying teacher. Let's try one more. 3/2, 2x plus 1 over 3, the 1/2. What am I missing? The chain rule. This is, I have to multiply it by 2. All right, so now I get the right answer. It's a fact of life that math teachers will tell you. There's this psychic field that extends about this far from the blackboard, and it lowers your IQ by about 50 points. Okay. And that was a simple example. Oh boy. Now, to complicate matters, the part of this I can show you some examples, but I can't really teach you how to know what the right substitution is. Worse than that, there isn't always a single right substitution. There's sometimes more than one substitution. Say I wanted to make what was under the radical simpler, so I made u 2x plus 1. I could have gone a step further. I could have said, well, let's make u square root 2x plus 1. That would make at least this part of the resulting integral even easier. Now, I want to find du here, but you can just figure it out directly, find what the root is. But it turns out you can do this trick. This is u squared is 2x plus 1. So if I find du dx here, that's 2u du is equal to, is that right? Equal to dx. Get rid of the 2. Then I want to do the substitution here. So this becomes square root of, this becomes u. And dx becomes u du, or u squared du. Okay, we go ahead and find the antiderivative. It's u cubed over 3. It's a constant. And we're going to substitute back, right? It's the same thing we had before. Wait a minute. Okay, so now it's obvious. 2x plus 3, 3 halves over 3 plus 8. If you get an answer 2 ways, it's going to be the same answer. But it's always possible you'll go down some alleyway and it'll just get abnormally complicated and not get to where you're going. That's the part I can't teach you. I can't teach you, well, how do you find the right substitution? The way you learn is you practice, you do some homework, and you make mistakes. And you say, well, that didn't work, and you get kind of a sense of these. All right, I guess we'll try some other examples just to give you a little flavor of what you can do with this. And let's see if this one works. Well, that looks a little like, you know, our log function. So we won't be surprised if there's a log function when we're done here, but we don't know quite what to do with this yet. But again, the obvious thing would be to set u equals square root of x, or u squared equals x, or 2u du equals dx. And substituting in, we get over 1 plus u times 2u du. I'm going to take the 2 out, just get it away. All right. Well, now we have something new, but we don't really know what to do with that. We don't know what to do with this either right away. Let me think back to the beginning of the lecture. I had 2 things I put on the board, part 1 and part 2, and even though it looks a little simpler than what I showed you in part 2, it fits the profile here. I can take u divided by u plus 1, u plus 1 minus 1, meter minus 1. So this becomes 2 times the integral of 1 plus minus 1 over u plus 1. And now this is starting to look like familiar territory here. This becomes u minus log absolute value of u plus 1 plus a constant. And again, we're going to go back to our substitution in reverse. 2 times square root of x minus log of absolute value of 1 plus square root of x plus a constant. I think it's worth repeating the exercise of checking this. Let's find the derivative. The 2 can stay outside. Derivative of the square root of x is 1 over 2 square root of x. Derivative of the log of something here is 1 over that thing times the derivative of this using the chain rule. So that's going to be 1 over 2 square root of x. And this will be 0. All right. 2's go away. And what are we going to do with this? I guess we want to put this over a common denominator. So I have to put this square root of x times 1 plus square root of x. So I'm going to get 1 plus square root of x in the numerator minus same thing, square root of x plus square root of x. 1. Well, 1 plus square root of x minus 1 is square root of x over square root of x times 1 plus square root of x. And of course, these cancel. So, where was it? Way back. Way back here, that's what I started with. It's almost always worth your trouble to check by finding the derivatives. It's generally much easier to find the derivative, it's much more straightforward than finding the antiderivative. So it's a good way to check your work. Yeah, I think this would be a good time to take a break. We're going to be looking at this a bit more, and there'll be some homework. We'll have a few more examples all back on. All right. Any questions right now? Let me change modes for a second here. Minute. So, and everybody, we can work together if you're near someone, but try this integral. Not necessarily something you want to use substitution for, but you could use whatever antiderivative skills you have on this. Give this a try. Just a wish. Okay, someone want to give me an idea where I might start with this?
I use the top, so it's on the top to u, and then I found the derivative for u.
Oh, you're gonna use substitution?
Oh, that was the way I attempted to use. That was what I attempted to use. And then
Okay,
I went down
and-
to,
What substitution did you try?
the u substitution, and I used x to the fourth power minus 4x. I said to u.
Okay.
And then I found du was 4x to the third minus 4 dx. And then I got dx equals du divided by 4x to the third minus 4. Yeah, u got x to the third.
I'm sorry?
U over x to the third. X to the third. Then I got du divided by 4x to the third minus 4.
Okay.
And then that's where I was at.
Okay. You're following my lead, and that's how you start. We've got all these x's here, right? We need to solve this with u, we need to get rid of the x's. Well, I'm not sure how to do that. I guess I could start by combine these. That'd be 4x to the 6 minus 4x cubed only, if only I didn't have this, then I could find x and then plug it in. Then that would make this kind of look kind of ugly. So this is one of the difficulties in learning how to do these is sometimes it does look that ugly and it's the right direction, and sometimes we kind of climb down a rabbit hole here. So I think we have in this case, but this is how you this is what you're going to do. You're going to try things. Now, also, you develop a little intuition about this. You look at this and go, wait a minute. Wouldn't this be simpler if I just divide out? Like x minus over x squared. Now that looks a lot simpler, doesn't it? Yeah, again, there's no, and thank you for giving us a start here, because we're never gonna know how to do all these right off the bat. All right, let's try a different one. Try x over +1/4. Now, work on this for a minute. Give you kind of a hint. Do what you need to. Okay. All right, I want to point out a feature that sometimes gives you a hint where to go with this. We're going to want to try and change all this over to some u. Like there's an x up here and an x down here to deal with. But sometimes, it's this combination here, in this case, x dx, or some piece of this, where when we find the u, we're going to want it to look like x dx. Well, again, it may not be obvious, but there is kind of a substitution here that would do that for us. If I say u is x squared plus 1, and du is just going to be 2x, which is pretty close, right? Du over 2 is x dx. So I can kind of swing this by substituting here du over 2, and here is u to the 4th, or again, taking the constant out, 1 over u to the 4th du. And that's pretty straightforward, right? This is, let me rewrite this. u to the negative fourth. And so we can use the reverse power rule, the u to the negative 3 over negative 3, and so forth. And then we just have to plug back in for u here. Now, we might as well go ahead and do that. We have, I guess it's negative 1/6, and this is 1 over u cubed, which means 1 over x squared plus 1 cubed. Now, as it turns out, the problem actually they wanted us to do here is a little bit more. They wanted this as a definite integral, which, okay, that's not that hard to figure out at this point. Negative 1/6. Plug in 1 over 2 to the third, 1/8 minus well, that's interesting. This turns out to be 0. There's a lot packed into this problem here. I wonder why. Well, there's something about this function here that may not pop out on you. So the denominator, we've got lots of 2's here, right? That ought to suggest something. When you're squaring things, or just squaring it into the fourth, you've got an even function here. I hope you all remember an even function. It's a function where f of negative x equals f of x. But here we've got an x on top. That's an odd function. Negative x equals negative f of x. And an odd function divided by an even function is an odd function. So we have an odd function here. And I don't mean peculiar, I mean that it's symmetric around the origin. So if we have a limb like this, and if we happen to have limits that are opposite, then the positive area is going to match the negative area, and you're going to get 0. That's just a little trick. You know, you could have a very complicated, ugly-looking expression that, you know, say, see something like this and you go, oh my gosh, how am I going to find an antiderivative? Well, you don't have to. I mean, here we have clearly an even function dividing into an odd function. The whole thing's an odd function going between the same opposite limits. This is going to be 0. This will not appear on the example. It's useful. say, well, here we got our function all the way back to x. But wouldn't it be nice if we didn't have to do that? I mean, what we're doing here with the substitution is we're changing the coordinates. Maybe there's a way that we could not just change the coordinates, but also change the limits. And in fact, we can. Yes, guess we're gonna backtrack a little. Recall we had this formula that says we have some integral f prime g of x times g prime of x dx, and you substitute u equals g of x, that becomes f prime of u du. Well, it turns out that if we're interested in a definite integral, and we have limits a and b, without converting back to x, we can call this limit g of a, g of d. Well, that might make things easier under some circumstances. Let's go back to that problem we started with. Integral square root of 2x plus 1. And we'll give it some limits. Say 1 and 4. And again, we'll do our substitution here. I guess we could just say u equals 2x plus 1. So du is 2 dx, or dx equals du over 2. And this becomes what? Square root of u times du over 2. Well, let's just go through it again the way we would have before, right? So x to 1/2. This becomes u to the 3/2 over 3/2. We still have a half here. Plus a constant. I hope you're watching, George, because I don't want to make the same mistake I did the first time. Oh, that gets rid of the 2, so that should be u to the 3/2 over 2, which becomes 2x plus 1 to the 3/2 over 2, which I can evaluate between 1 and 4. All right, let's see if we can do that. So that's 9, square root of 9 is 3, cubed is 27 over 2, minus well, this will come out nicer. Square root of 3 cubed. All right. Be the square root of 27 over 2. Hope I got that right. But we could have stopped here if we figure out what g of a and g of b is. Well, g is our u. So this makes our limits 4, 8, 9, and 1, 3. See how that works. So it's 9 to the 3/2 minus 3 to the 3/2 over 2. It's the same thing. So again, you have a choice here if you have a definite interval. Sometimes it'll be easier to just convert back to x. You can always do that, but you can skip a step if you use this formula and you convert the limits. We have a bunch more to do here, but I can't help kind of digressing. What are we doing here? We have some function square root of 2x plus 1, so it's going to be something like this. Our f of x. X. This is the x-axis. And we somehow, using this technique, substitution, we convert this to some other function. I guess it's similar, but now our coordinates are, here they're x and here they're u. And even though we've changed our coordinate system, we're integrating over a different area, we get the same value. There's something that doesn't change here. It's kind of immutable. No, I can't go there. It would be too much fun and it would be too disturbing. All right, well, all right, so let's put this in a box. This is not calculus. This is just so you can impress your parents and friends. So there's this theory you've heard of or run into, or you will somewhere. You won't understand it, just the same reason I won't understand it. It's way too complicated, but it's called general relativity. You know, the big theory that Einstein came up with after his special relativity, and has to do with gravity. You know, things orbiting here. I guess this is the sun, there's the earth. You've got the moon going around. And it superseded theory by Newton. Newton of calculus fame. And what's at the heart of it is this idea of changing coordinate systems. So his idea is, instead of treating this the way Newton did, which is these are massive bodies and they pull each other together, he said, what this mass here does, and I'm sure you've seen this kind of diagram, which is kind of a fake diagram, is that you have a massive body here, it kind of distorts the coordinates, distorts time and space. So, you know, if you think of this as kind of a, there's the sun and there's the earth, kind of rolling around, it's just rolling around this, you know, depression here, it's kind of stuck in it. And from its point of view, this is kind of this is a straight line, this is what we call a geodesic. So, all right, I don't want to confuse things too much. I just, you know, this idea of changing coordinates is a very powerful idea. It's just at the heart of this very basic theory that turns out to be more accurate than Newton's theory. Right. I'm sorry. I think that was a little respite. If you're not interested in physics or astronomy or relativity, that's fine. It's not part of this class. All right. So definite integrals and substitution. Let's try an example. Let's have you try an example. This will not be an example where it magically turns into 0. Again, you can use either the complete formula, where you switch the coordinates, or you can switch back to your x coordinates and use the original limits. Let's try that for a few minutes. I guess I'm gonna add a hint here. If you haven't thought of it already, try u equals x plus 4. See how that works. let's try and step through this then. Let's just think of this as an indefinite integral to begin with. So if this is our substitution, okay, du is just dx. So what is this going to become? It's going to become square root of u, and then the dx is going to become du. Well, but we've got x up here. What can we do with that? Because we want u's, right? Anyone have any thoughts on this? Yeah, minus 4 is x. All right. Well, now what can we do with that? Well, how about we break this up? No. This is u to the 1/2 minus 4 u to the minus 1/2 du. Well, that should be pretty easy, shouldn't it? U to the 3/2 over 3/2 minus 4 u to the 1/2 over 1/2. I'm just going to leave it like that. So let's go back and look at our limits here. How do they change? Well, these are x. X plus 4 is u, so that's 4. 4, x plus 4, that's 8. So you just have to evaluate this between 8 and 4. I'm tempted to deal with the fractions, but I don't want to quite yet. So, okay, u is 8 squared, well, cubed is, see, this is 2 to the 3rd times 3/2. 2 to the 9/2 over 3/2 minus 4. Again, u to the 1/3. Oh gosh. U to the 1/2. 2 square root of 2. Yeah, you know, I'm tired. I'm really tired. You just have to plug in 8 here and subtract what you get and plug in 4. Maybe that wasn't the thing to do. Maybe I should convert this back to x. X is x plus 4 to the 3/2 over 3/2 minus 4. X plus 4 to the 1/2 over 1/2. And the original 0. So we get 4 to the 3/2. 3/2 minus 4 times 4 to the 1/2. I can handle that. Minus, wait a minute, what did I just say? 0? This is what I'm subtracting. 3/2 minus 4 times 4 to 1/2. 1/2. And over here, again, it's going to be the same ugly fractions. Well, we have an algebra problem here. I'm not going to worry about that. Now, one nice thing you can do with these problems, after you've worked really hard and figured them out, solved the radicals, is you can always type in the equation, original equation here. Where are you? X over square root of x plus 4 into your y equals in your calculator, and use the calculator to do a check. It's a nice, easy check. If it doesn't come out in integer, then you wouldn't use this to solve it in the first place. I mean, in this case, we're going to end up with some radicals, but you can use this to check, see whether those radicals are the value it gets, and that will tell you if you got the answer correct. All right, I'm going to end today. We're going to do some more with substitution. We have a little bit more to go over in this class before we round up. I guess I'll wait till Thursday to post the homework assignment. That'll be the last homework assignment for the semester. All right.